Okay. Hello guys, welcome to the lesson of DBA from Introduction to Practice. I'm your old friend Peng Wang, the global technical evangelist for OceanBase. Today our lesson is the diagnosis and tuning of OceanBase. The content we want to introduce to you in this lesson is mainly related to SQL tuning. Let's get started. This topic contains a lot of materials, so we will divide it into two lessons. The first lesson contains ODP SQL routing principles, managing database connections, analyzing SQL monitoring views, read and manage SQL execution plans. Let's go into the first chapter. The picture on the right was shown when introducing the overall architecture of OceanBase. At the top of the architecture is a component called 𝘤𝘐𝑝roxy. Actually, 𝘤𝘐𝑝roxy is ODP. In the previous lesson on the architecture introduction of OceanBase, it was said that 𝘤𝘐𝑝roxy is a proxy server dedicated to the OceanBase database. The user's data will be stored in multiple copies on each OB server node. 𝘤𝘐𝑝roxy receives the SQL request sent by the user, and then forwards the SQL request to the bachelor target OB server node, and finally returns the execution result to the user. Now, here is the question. Accessing the database through the ODP involves an extra step compared to directly connecting to OB server. So, why is ODP needed? Let's take a look at the architecture first. The app is our business program. There are 3 ODPs under the app. In actual deployment, there is usually a load balancer such as F5 or NGX between the ODP and app to distribute requests to multiple ODPs. And the ODP is the OB server node. There are 6 OB server nodes in the architecture. The first reason for using ODP is that ODP can obtain the data distribution information of the OB server node and forward SQL to the machine where the data is located more efficiently. In this way, the execution efficiency of SQL will be higher than sending SQL directly to the OB server, and then executing a remote plan on the OB server. We will talk about what a remote plan is in a moment. The second reason for using ODP is that if the frequency of machine offline and online operation is relatively high during the operation and maintenance process, or if an OceanBase cluster is large in scale and has a large number of nodes, it's an environment where machine fails are more likely to occur. In these scenarios, the client will be disconnected if the client is directly connected to the OB server node that is offline or has a machine fail. However, ODP shows the complexity of the distributed nature of the OB server node. When client connects to ODP can guarantee the stability of the connection. In other words, ODP allows users to use the distributed database like a standalone one. In this section, we will mainly introduce the routing strategy from the performance aspect. First, let's introduce some background knowledge. The first background knowledge is ODP routing. What is the implementation logic? The first step of the ODP routine is to parse SQL and extract information. When parsing SQL, it uses ODP's custom parser module, which only needs to process the database name, table name, and hints in the DML statement. Compared to the OB server's formal parser module, it's much lighter, resulting in higher parsing efficiency. The second step is to obtain local information through the routing table. ODP will obtain the location information of the table or partition involved and its replica based on the SQL. For example, if the table is partitioned, ODP can determine which partition contains the data to be accessed by analyzing the filtering conditions. And then, it will directly obtain the location information of the node where the replica of the partition is located through the location cache. ODP will first try to obtain the routing table from the local cache. If it cannot be obtained in the cache, it will initiate an asynchronous task to obtain the routing table from OB server. The third step is to determine the routing rules. ODP needs to determine the best routing rules according to different situations. If the OceanBase cluster is deployed in multiple locations, ODP will also provide LDC routing, which gives priority to nodes in the same computer room, followed by nodes in the same city, and finally, nodes in other cities. The last step is to select a suitable OB server node from the obtained routing table according to the determined routing rules, and forward the request to the target node after checking the blacklist. We just mentioned that one of the functions of ODP is to avoid the frequent generation of remote plans, and to make it generate local plans as much as possible. The second background knowledge we will introduce next is several types of plans in OceanBase. In OceanBase, partition is the basic unit of the data storage. When we create a table, there will be a mapping between the table and the partitions. If a non-partitioned table is created, one table corresponding to one partition. If a partition table is created, one table may correspond to multiple partitions. In OceanBase, an execution plan is generated before SQL is executed. The executor schedules different operators to complete the calculation according to the execution plan. There are three main types of plans. They are local plan, remote plan, and distributed plan. Below, I will take the default strong consistency read as an example to introduce these three different plans. Strong consistent read means that the leader copy of the partition needs to be accessed during the query process. The meaning of local plan is that the leader copies of all partitions involved in the SQL statement are on the OB server where the current session is located. During the execution of the entire SQL statement, there is no need to interact with other OB servers. This is the simplest scenario, as shown in the figure. The proxy directly sends a SQL statement involving only T1 and T2 tables to this node. It happens that the later copies of these two tables are also on this node, which will generate the local plan on the right. The second type is the remote plan, where all the partitions master copies involved in the SQL are located on a different OB server than the one hosting the current session. In this case, the OB server must forward the SQL or subplan to the appropriate OB server. Generally speaking, the plan generated by the explain command for remote execution will look like this. Let's take this remote plan as an example. In this plan, the operator 0 and 1 exchange in and out remote are used to split the work done on different OB servers. The OB server node where the operator 0 is located receiving the SQL routed by the ODP is responsible for generating the remote plan and forwards the complete SQL or the subplan composed of the operator 1 to 4 to another OB server node where the partition master is located. The OB server node where operator 1 to 4 are located is responsible for calculating their 𝘖𝘤𝘬𝘢 join and returns the calculation result to the OB server node where the operator 0 is located through the operator 1. Finally, the OB server node where the operator 0 is located receives this result and continues to return the calculation result to the client. In general, local plan and remote plan are both single partition routing. The rule of ODP is to minimize the use of remote plans with poor performance and whenever possible, reroute the local plans that offer better performance. Let's think about the root plan. Why is its performance so poor? Because it has an additional RPC forwarding. As you can see in the figure, the forwarding may be a plan that has been generated, or it may be the original SQL. If the forwarding is a plan, because the data structure used to describe a plan is very complex, the network transmission overhead will be very large. If the forwarding is SQL, the network transmission overhead is indeed small, but a SQL analysis must be done to generate a plan through SQL. After sending it to another node, another SQL analysis must be done to generate a plan. The SQL analysis will perform a complete parser and resolve process. And it's also necessary to rewrite SQL and select the best execution plan in the optimizer module, which is also very expensive. Although the optimizer will evaluate which scenarios are better to forward the plan and which scenarios are better to forward SQL. No matter what is forwarded, it's better to directly generate a local plan. For ODP SQL forwarding, only a lightweight SQL analysis and simple partition information retrieval are required. This process is significantly more efficient than forwarding a remote plan generated by an OB server. This is one of the reasons why ODP is still used. The third type is the distributed plan, which is often the case when the partition master copy spans multiple machines. The plan generated by the explain command for distributed execution plan may look like this. The master copy of multiple tables involved in the SQL statement are distributed on the multiple different nodes. In this way, when generating a plan, the data needs to be redistributed. Finally, I repeat why we need to introduce the plan type. The plan type because the ODP has an important feature that it can avoid generating remote plan and allows you to generate local plan with higher execution efficiency as much as possible. Next, let's talk about the high availability of ODP. High availability means that the database has the ability to tolerate machine fails, making the fails transparent to the application. If the ODP finds the OB server node is faulty, it will exclude the faulty node during the routing and select a healthy node instead, which has a certain retry compatibility for the SQL being executed. High availability involves faulty detection, blacklisting, retry logic, and others. We will not go into details about this today. You can see the feature in the slide. After ODP finds OB server 1 is faulty, it will add this node to the blacklist. And then a healthy node will be selected during routing. ODP implements cluster routing, tenant routing, and intra-tenant routing. Cluster routing simply means that through one ODP, SQL can be forwarded to multiple different clusters. So ODP, different machines of different tenants in different clusters can be accessed. Let's talk about the cluster routing first on this page. Cluster routing means that the ODP routing function supports access to different clusters. For example, if OCP manages multiple clusters, ODP will obtain the mapping relationship between the cluster name and RS list through OCP. The RS list here does not need to include a list of all machines in the cluster. ODP will obtain all machines in the cluster through access rules. Generally, RS list is the machine where the root server is located. From this figure, we can see OCP is a very important module for cluster routing. When cluster routing problems occur in the production environment, most of them are caused by problems with the OCP module. ODP obtains RS list from OCP when a user logs in to access the cluster for the first time and save it in the memory. When the cluster is accessed later, it can be obtained from the memory of ODP. Please note that since ODP routing function supports access to different clusters, when connecting with an ODP in the command line, you need to specify the username, tenant name, and cluster name. Similarly, if some tools like ODC connect through ODP, the cluster name should also be included in the connection string configured for these tools, just like the connection string in the figure. If you connect directly to the OB server instead of ODP in the command line, you only need to specify the username and tenant name. And you cannot specify the corresponding cluster name. just like the connection string in the figure below. After ODP completes the cluster routing, it can obtain the RS list on the cluster. Taking the sysTelnet as an example, ODP will log into a machine in the RS list and obtain all the node information of the cluster through the 𝘙𝘂𝘏𝘐𝑏𝑎𝑜b servers. ODP will save the obtained tenant information in the local memory and update the cache information according to the certain strategies. For the sysTelnet, the latest information is obtained through the local cache every 15 seconds. For ordinary tenants, the refresh frequency of ODP is not high. Similar to lazy loading and optimistic locking. OB proxy will only reaccess an internal table in the OB server to retrieve routing information for regular tenants when the cache is not used. And the OB server retains a specific error node. The diagram on the right is the same as the routing principle just mentioned, so we will skip it here. The next part is managing database connection. For standalone database, there is only one physical connection between the client to the database, right? However, when a connection is established through ODP and OceanBase, there will also be a physical connection between the client and ODP. Because OceanBase is a distributed database, the cluster may be composed of multiple nodes, so there may be multiple physical connections between ODP and OB server nodes, as shown in the figure. We refer to the connection between the client and ODP as the client connection, and the connection between ODP and the OB server nodes as the server connection. When the data accessed by the client exists on different OB server nodes, ODP will establish multiple physical connection with OceanBase. And there is only one logical connection from the client's perspective. ODP is based on this point to achieve these functions mentioned above, such as shading back-end exceptions. The slide will introduce some common operations of client connection. When connecting to the database through ODP, you can see we can use show proxy session command and the sysTelnet to view the internal status of all client connection to the current ODP. For example, the second row in the table is a connection to the test database and the MySQL tenant. The proxy session ID in the first column is the session ID between the OB server and ODP, which is the equivalent to the server connection ID. The ID in the second column is the ID of the client connection recorded by ODP. So the two IDs are different. When connecting with ODP, you can use these statements to view the detailed information status of the specified client connection, including the server session involved in the client connection. When ID is not specified, the detailed status of the current session is displayed. When ID is specified, the value of the specified attribute name can be searched by like, as shown in this example. Currently, OceanBase does not support directly waiting server connection through ODP. You can use the root user to log into the systenant of the OceanBase to view all servers in the cluster, and then directly connect to the corresponding OB server node to view the connection. For example, we can see the root user to log in to the systenant to view all servers in the cluster. Select the OB server node you want to view and connect directly to the OB server node. Then execute the show process list command to view all connections involved in the current OB server node. The next part is analyzing SQL monitoring views. OceanBase's system views are divided into two categories. One is a data dictionary view, and the other one is a dynamic performance view. This feature is a schematic diagram of the OceanBase dictionary view. The data dictionary view displays the basic information of the database objects managed by the system tenants. In addition to the views compatible with MySQL, the OceanBase specific view naming starts with DBA and CDB. Views starting with DBA displays information for each tenant, while views starting with CDB are dedicated to the system tenants and provide the database status of all tenants within the system tenant. Typically, each DBA views have a corresponding CDB views under the systenant. Our topic today is SQL tuning. So we will focus on introducing SQL performance monitoring views. Here, we will introduce two of the most commonly used monitoring views. One is 𝘔𝘁 SQL audit, and the other one is plan catch, plan explain. Dynamic performance view displays the status information of the system dynamic changes. The naming characteristics start with 𝘔𝘁 and 𝘂. 𝘂 only displays information on the specific nodes logged in, and 𝘔𝘁 displays information on all nodes. Another point to note here is that the dynamic performance view and the user tenant can view the information of the current tenant, and the dynamic performance view of the systenants can view the information of all tenants in the entire cluster. SQL audit is a view used to analyze the execution of SQL. It will record the information related to the SQL that has been executed as a basis for performance optimization. As long as the SQL is executed regardless of success or fails, various key information during the execution of this SQL will be recorded, which is very helpful for diagnosing SQL problems. In scenarios where we don't have extremely high requirements for execution performance, we recommend turning on the SQL audit and appropriately increasing the available memory limit of SQL audit. Why do we recommend that you appropriately increase the memory? Because the data of 𝘔𝘂𝘶𝘭𝘰𝘶𝘥 is stored in the configured memory space. Each tenant has an independent cache on each node. When the memory usage of the number of records reaches the upper limit of the elimination, automatic elimination will be triggered, and the oldest data will be eliminated first. SQL audit data has an elimination mechanism. DBAs often turn off the SQL audit function first when troubleshooting SQL problems. Why? Because after that, no new data will be recorded. After turning it off, it can prevent the monitoring data corresponding to the SQL from being removed, and can effectively save the scene. Next, let's briefly introduce how to turn on and turn off SQL audit. The command is very simple and needs to be executed using the sys tenant. It takes effect on the entire cluster and the default value is true. If the cluster switch is turned on, you can also use the tenant level system variable to more finely control whether SQL audit is enabled for a specific tenant. There is also a tenant level system variable which can be used to control the persistence of tenant memory occupied by the current tenant SQL audit function. The default value is 3. Why do we need the system variables? This is because the memory used by SQL audit cannot grow indefinitely. Therefore, we need the automatic elimination mechanism we just mentioned. There are two types of elimination mechanism for SQL audit. One is automatic elimination and the other is manual elimination. The automatic elimination rule is written in this table. The SQL audit memory limit in the table is the maximum available memory allocated. The elimination rules will be different in memory limits, but the overall rules are: first one, when the actual memory usage of SQL audit reaches the specific threshold, elimination will be started. The second one, when the actual memory usage of SQL audit drops to the specified threshold, elimination is stopped. In addition, SQL audit supports manual elimination at the tenant level. The elimination method is to executing the following command and the sys tenant. There are many fields in 𝘔𝘂𝘵 SQL audit well. Here we simply list a field. For example, we can see what the plan ID of this SQL is. Does SQL hit the plan catch? We will talk about the plan catch later. And what's the SQL plan type? Is it a local plan, a remote plan, or even a distributed plan? In addition, you can also see the time intervals of some important events in the SQL audit wheel, such as net time, net wait time, kill time, dedicated time, and others. You can refer to the OceanBase official website to get a detailed description. We can use these timestamps to identify which stage of a slow SQL query is causing the delay, and then further analysis why that particular stage is slow. Next are the usage examples, which are several commonly used related cycles. First, there are slow SQL statistics, which query cycle is that exceed a certain threshold within a given time. You can then optimize specific SQL queries based on the results. This example uses SQL audit to view the SQL involved in a transaction. Each SQL entry in SQL audit is expected to record the transaction hash, a unique identifier for the transaction associated with the current SQL. This field can be used to retrieve all SQL information for the current transaction, allowing you to access whether the transaction module in the business stress test meets expectations. Query the SQL statement that consume the most tenant resources and sort them in descending order by the product of execution time and execution count. If the tenant currently has insufficient capability, this statement can be used to determine whether it's a SQL problem and what the specific SQL is. Of course, things like top SQL and slow query can also be directly displayed on a GUI through OCP. So, if you use OceanBase in a production environment, it's recommended to deploy OCP. Next, I will introduce two performance views. One is SQL audit, and the other is the monitoring view of 𝘔𝘂𝘶 plan catch, plan explain. OceanBase's optimizer uses many rewrite rules and a complex algorithm, making it powerful but also increasing plan generation time. In a TP scenario, a primary key query might take 1 millisecond to generate a plan, while execution only takes half a millisecond. If a new plan is generated for each query, most of the time is spent on this. To solve this, OceanBase introduces plan catching, allowing similar SQL queries to share the same plan. Upon receiving a SQL request, the first parser module performs normalization on the SQL, replacing consistent parameters with the white card. It then checks the plan catch to see if a plan for the normalized SQL already exists. If a generated plan is found in the plan catch, it will be executed directly. If no available plan is found, the normal parsing process will be followed to regenerate the execution plan for this SQL, and save the generated plan to the plan catch for subsequent SQL to use. Using the plan catch can greatly reduce the time to obtain the execution plan, thereby reducing the SQL response time. Now, here is the question: how can we use these two plan monitoring wheels to confirm the actual execution plan of a specific SQL statement? When the same SQL statement is executed repeatedly, the execution plan may change due to the factors such as changes in database objects, statistical information, or ROB server's version. Therefore, to determine the actual execution plan for a specific SQL statement, you should not rely solely on the explain statement, but query the two plan monitoring wheels, 𝘰𝘂 SQL audit and 𝘔𝘂 plan catch plan explain, to confirm it. We have another question: how can we use these two plan monitoring wheels to confirm the actual plan execution plan of a specific SQL? First, you need to query the fields tenant ID, server IP, server port, and the plan ID corresponding to this SQL, because when you query this plan catch wheel later, you need to specify the equivalent conditions of tenant ID, server IP, server port, and the plan ID. Otherwise, the query result will be empty. After specifying these equivalent conditions, querying this will to get the actual plan of the corresponding SQL when it's executed. The 𝘰𝘂 plan catch plan explain will records the detailed information of the execution plan. Its main fields are introduced are follows: plan depth, operator, name, rows, cost, and properties. Because the detailed information here is too long, so the screenshot only captures the beginning. Here, let's take a look at show create wheel. This command queries this wheel is equivalent to executing the SQL statement, which performs a join between the old database and tenant virtual collection tables. The next part is about reading and managing SQL execution plans. For OceanBase user, the most commonly used command to view the plan is explain. The information displayed by explain can help you understand how the plan is executed. Here is a simple example that creates two tables, inserts a batch data, and then performs a join operator on the two tables. The output of OceanBase explain command is divided into two parts. The first part is the tree structure displayed on the execution plan. The level of each operation in the tree is distributed by the indentation of the operator in the plan. The deepest level is executed first. The deeper table scan is executed first to read data from the storage layer, and then the Hershey join on the upper level is executed, and the data split out by the two table scan operators is used for join calculation. Operator 0 in the plan is a Hetch join operator, which has two child nodes. They are operator 1 and 2. The execution logic of Hetch join operator 0 is read the data on the left child node, that is, the row split out by the table scan operator 1, and then calculate the Hetch value based on the join column to build a Hetch table. Read the data on the right child node, that is the row split out by the table scan operator 2, and also calculate the Hetch value based on the join column, and try to use the Hetch table built by the left branch data for Hetch detection to complete the join calculation. If a table operation is involved, the name fields show the table names. Estimated rules is the optimizer's prediction of how many rows the operator will output to the next level. Based on statistics, estimated time is the estimated execution time for operator. These values are approximation and should be used as references. The second part of explain command output is outputs and filters, which contains detailed information about this operator, including output expressions, filter conditions, partition information, and unique information about these operators. Output shows the output expression of the operator. Filter displays the filter predicate of the operator. If no filter conditions is set, it will be null. There is also a row stat equal to 256 in the plan, which is related to the vectorized execution technology of the OceanBase execution engine. It means that in a specific operator, calculations will be performed in batches of 16 rows. This batch method will reduce the overhead of some function calls compared to the row method, and can also use some SIMD acceleration for optimization, which is vectorized calculation in the vectorized execution engine that we often mention. The following content is related to the index on this table. To better understand the second part of each operator in the OceanBase explain, users should first familiarize themselves with the role of each operator. Information about common operators in the plan can be found directly on the official website. In addition to the explain command, there is explain extended no address, which provides a more detailed execution plan. Extended shows additional information compared to explain. No address will hide the address information in the plan, which is mostly useful for developers. We recommend you using no address with explain for troubleshooting SQL performance. When extended is added, you will see extra details such as hint information, query block, outline, optimization information. For cycles involving a single table like T1, you will see information like table rows, physical range rows, and logical range rows. There are also some other plain information displayed, such as index back rows, output rows, table DOP method, available index name, unstable index name, and others. You can check the detailed information on the official website. Please note, additional details like default parallelism is 1 if no parallelism is set. This chart introduces optimization for you, and you can review it after this lesson. Let's take a look at difference between explain, extend, and explain. Explain extended no address. Explain extended will also display the address information of the data stored in each expression involved in each operator. Generally speaking, the display mode is only used by technical support when troubleshooting SQL correctness issues. Generally, users do not need to care about the address information corresponding to each expression and can ignore it directly. This looks much messier than no address, with address information that users don't care about everywhere. So it's recommended that users add an extra no address when analyzing the problems. If you can understand the operator in the plan, you can know what OB server does to execute this SQL. We recommend users visit the OceanBase official website to learn about the most common table scan and join operators, as well as DOS execution in table scan. Here we take the table scan operator as an example to show you how to use the operators in the tables in the plan to understand what the OB server doesn't execute this SQL. For example, the table get operator is a special type of the table scan, which means that the query uses the primary key. Table T1 has 3 columns, C1, C2, and C3. The primary key is in column C1, and the index in column C2. If the filter conditions is C1 equal to 1, the primary key will be used. The following range condition describes the range of the scan on the primary key. Look at this SQL statement. The projection column to be queried is C2, and the filter condition is C2 equal to 1. Because there is an index on C2 column, you can see that the query uses the IDX index in the planned name field. In the query range at the bottom, you can see that the range scanned on the index is the range of C2 equal to 1. And there is also an index back flag that is false. The reason is that only the C2 column is queried, and the index already has the data of the C2 column. So there is no need to go back to the main table to check other content. if select C2 is changed to select star, the filtering condition remains unchanged because there is no C3 column in the index. It's necessary to return to the main table to query the data in the C3 column. Therefore, compared with the plan on the previous slide, the index back to the table flag becomes true. If the filtering condition is changed to C3 equal to 1, because there is neither a primary key nor an index on column C3, the information of the IDX index cannot be seen in the name. At this point, a full table scan is required. During the full table scan, the query range is from mini to max, and the scanned data needs to be filtered once. In the plan, it can be seen that the condition for filter is C3 equal to 1. So far, everyone can basically understand the plan related to table scan. It's very simple, right? Most other common operators, such as join, sort, and group, are easier than table scan. You can check them on our OceanBase official website. Table scan also has a form called DAS, DAS, which stands for Data Access Service. The symbol in the plan is the addition of a distributed before the table scan operator. If the data distribution crosses nodes, resulting in a distributed query, but the query result site is relatively small. In such a scenario, instead of transmitting the subplan to other nodes through the network and executing the subplan on other nodes, it's better to directly pull the data from the storage layer of other nodes, so that the network transmission overhead will become smaller. DAS provides such a remote interaction capability with the storage layer of other nodes. It does not perceive the specific semantics of SQL, and only provides a capability to directly access the storage layer data on the remote node through RPC. In the last course, when we talked about the global index, we said that partitioning method on the global index is different from that of the main table. So when the global index is returned to the table, it's easy to have cross-node data access. The plan in the figure is such an example of a global index returned to the table. You can see that this table scan operator uses DAS. Next, let's talk about how to manage execution plans. One of the most commonly used methods is hint. Users can use hints to control the optimizer and let it generate a specified execution plan. Generally, the optimizer will select the best execution plan for the SQL query, and the user doesn't need to specify it using hint. However, in some scenarios, the execution plan generated by the optimizer may not meet the user's requirements. In this case, the user needs to use hints to specify the generation of a certain execution plan. One thing to emphasize is that hints only affect the execution plan generated by the optimizer and will not affect the original semantics of the SQL statement. For example, the hint is used to specify the SQL execution parallelism as 3. You can see that DOP equal to 3 is displayed in the explain command. You can see a note degree of parallelism is 3 because of the hint shown in the explain extended no address command. From this table, you can see the hint parameter names, semantics, and descriptions. There are many types of hints. Please refer to the official website after this lesson for details. Hints often require you to specify a query block name. Next, let's talk about what the query block in the hints does. In a DML statement, each query block has a QB name, which can be specified by the user or automatically generated by the system. Each query block is a semantically complete query statement. SQL is extracted and structured according to the words select and delete, and then numbered from the left to right. When the user does not specify QB name with hint, the system will generate it from the left to right in the order of cell $1 and cell $2. The first QB name in the hint is used to locate which query block hint applies to. Here we use a hint to specify that the outer T1 table is the primary table and the inner T2 table is the index. You can see that in this plan, there are no brackets and indexes after T1, but there are brackets and indexes after T2, which means that the hint is effective. You can go back to the previous slide and compare the name column in the plan to see what the hint does. The index primer here has the same effect as full on the previous slide, as shown in the outline data on the right. The used hint is the one specified by the user, while the outline data fully describes the SQL plan. As you can see, the index primary is effectively rewritten as full in the outline data. Hint in the above example can also be written in the following three ways, which are equivalent. What do the second and third writing styles mean? What I want to express is that if you want the hint to apply the current query block, you don't need to explicitly write what the query block name in the hint is. It defaults to the current query block. For a hint without a specified query block, it will be applied to the query block where the hint is located. In the SQL statement, since the hint is written in query block 1, but the T2 table in the hint only appears in query block 2, you can see that the hint cannot take effect. T2 does not use the specified T2 C1 index, but uses the main table. Next, I will tell you a few commonly used hints. The first one is index hint. First step, create a table T1. Index IDX1 is created on column C1. Index IDX2 is created on the column C2. And then, a batch of data is inserted. The data in column C1 is 1, 2, 3, 4 to 1000. And C2 is the remainder of the row number divided by 3. Execute such a cycle C1 equal to 1, C2 equal to 1. The optimizer will choose the index IDX1 because C1 equal to 1 has a higher filtering property. But we can force the plan to select the index IDX2 by specifying hint. It should be noted that it should be noted here that in the SQL statement, if the table name has an alien, the table aliens must be written for the index hint to take effect. The second commonly used hint I want to introduce is leading. The function of the leading hint is to specify the join order of the tables. In the figures example, if the join order specified by the hint is D, C, B, A, then D and C are joined first. The result is joined with B, and the result is joined with A again. In table name list, you can also use the bracket to indicate the join priority of each table, so that you can specify a more complex join order. For example, writing it this way ensures that D and C are joined first, followed by B and A. The results of the two joins are then used for the finally join. The next commonly used hint is the join hint, which can specify what kind of join method to choose for calculation, such as nested loop join, merge join, or Hershey join. This is the syntax of the join hint. Taking nested loop join as an example, table name list can be in the following forms. You can review them after this lesson or refer to the official website for details. Let's take an example. Create 3 tables firstly, T0, T1, and T2. If you want the join order to be T0 joined with T1 and then joined to be a nested loop join, you should write it like this. If you want the join order to be T0 joined with the result of T1 joined with T2, and you want the outermost join to be a nested loop join, you should write it like this. The 3 hints use NL, use Hershey, and use merge are often used together with the leading hint. This is because only when the right table of the join matches table name list, a plan will be generated according to the hint semantics. Let's take an example. There are 6 original planned spaces. If the hint is added, the plain space is reduced to 4 times. And at last, if the hint is added, the plain space will be determined. The same is true for Hershey join and merge join. Both specify a table as the right table of join, so I will not go into details here. There is also an outline for managing SQL plans. We can create an outline and then write in the outline. Then, when executing a certain SQL, a certain set of hints will be automatically selected. For outline content, I remind you to visit the OceanBase official website. Okay, if you have any questions, now is the perfect time to ask. Let me check the QA channel. Okay, it seems no questions here. Okay, before we wrap up, I'd like to remind you that our next lesson will be next Thursday evening, where we will be covering the second part of this lesson. We look forward to seeing you then. You can also reach out anytime through our OceanBase GitHub or Slack community for further assistance. We are always here to help. We will be sharing how you can access the course materials and today's presentation slides in the comments section of this video. All the resources are free. Don't forget to subscribe to our OceanBase YouTube channel and join our community to stay up to date and get involved with us. See you guys. Bye-bye.